Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 18: Phi compiler design and scale bridging, from intention to actuators. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once: time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and the motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We are at the climactic edge of Book 10.3, Phi Programming. We have the language to write our dreams. We have the debugging loop to correct them. We have the OS to run many safely. But these dreams are still trapped in the world of symbols. Now, we perform the ultimate translation. We build the bridge from the abstract to the concrete, from the thought to the thing. We design the Phi compiler. You are entering the translation vault. It is a quiet, focused space where high-level intentions meet the gritty reality of hardware limits, transfer functions, and energy constraints. Your console here shows two worlds. On one side, the elegant human-readable Phi program. On the other, a sprawling time-stamped list of voltage levels, laser pulses, magnetic field strengths, and mechanical movements, the raw commands for the foundry's actuators. Your new skill is that of the compiler engineer. You're learning to build a faithful, optimized translator that turns create a vortex into the precise dance of 1,000 physical elements. Scene: the translation vault. The room is silent, save for the gentle hum of cooling fans. Before you, a hologram splits the space. On the left, a Phi program glows in clean, structured text. Create water. Target equals focus point. Frequency equals 1 kilohertz. Waveform equals sinusoid. It is simple, intentional, beautiful. On the right, a cascading waterfall of data streams, a matrix of numbers representing an array of 256 by 256 pixels on a spatial light modulator, each pixel's value changing nanosecond by nanosecond. Below that, a graph of current versus time for a coil, a temperature profile for a cooling system. This is the actuation sequence, the machine language of the foundry. Between these two worlds hangs a third display, the mesoscopic simulator. It shows a real-time prediction of what the actuation sequence will actually do to the Phi field, given the known imperfections, delays, and crosstalk of the specific hardware. It is the compiler's own digital twin, but for the control path. Our puzzle is profound. How do we automatically, reliably, and optimally translate the high-level description of a desired Phi pattern into a sequence of low-level control signals that will, when fed to imperfect physical actuators, produce that exact pattern in the real world? This is the art of scale bridging, leaping from the macro intention to the nano action. The language role, the translation skill. This part teaches a bridge-building skill. Specifically, it is the skill of faithfully mapping abstract grammatical constructs onto concrete physical operations across scales of description. Our core question about Phi is, given a target Phi pattern described in the high-level language and a specific set of physical actuators with known and limited influence on the Phi field, what is the optimal sequence of actuator commands that minimizes the error between resulting and target Phi while respecting all hardware and safety constraints? We are moving from speaking the language to building the mouth that pronounces the words. The anchor image, the conductor score, and the orchestra. We will use the anchor image of a musical conductor and an orchestra. The Phi program is the conductor score. It says, flutes play a rising scale here, violins sustain a chord there. The compiler is the orchestrator. The orchestrator's job is to translate that score into specific playable sheet music for each instrument, the flute part, the violin part, accounting for each instrument's range, timbre, and technical limitations. The foundry's actuators are the instruments. The mesoscopic simulator is the rehearsals in the conductor's mind, predicting how the orchestra will sound. The goal is a performance, the output phi field, that matches the conductor's intention. The coherence selection principle in compilation. In compilation, coherence is about constructive interference in the control domain. Constructive resonance, alignment, in compilation means that thousands of tiny actuator commands are precisely timed and shaped so that their individual effects on the phi field add up to the desired macro pattern. They work together, not at cross purposes. Destructive resonance, dissonance, means actuator commands are poorly coordinated. They fight each other, creating canceling waves, exciting parasitic resonances in the hardware, or producing chaotic transients that never settle into the target pattern. The compiler's mantra: if coherence breaks, we stop. If coherence returns, we continue. If the mesoscopic simulator shows that the compiled commands will produce a disordered or unstable field, the compiler must reject that compilation attempt and try a different optimization path. The core mechanisms, the compiler's threefold work. A phi compiler performs a sacred threefold task. 1. Modeling the hardware, the transfer function. The compiler must have a mathematical model of how each actuator influences the phi field. This is the transfer function. If you apply a voltage V to speaker element number 47 at time t, what change in phi, delta phi, does that produce at location xyz at time t plus delay? This model is built from first principles physics and calibrated with HLS data from the foundry from 1025. It includes actuator response, linearity, saturation limits, slew rate, how fast it can change, hysteresis. Crosstalk, actuator A's signal leaking into actuator B's effect. Propagation delays, how long it takes for the influence to travel through the medium. This model is the compiler's map of the territory between command and consequence. 2. Solving the inverse problem, optimization. This is the heart. The compiler is given a desired effect, target phi field. It must find the causes, actuator commands, that produce it. This is an inverse problem. It is solved by optimization. Cost function. The compiler defines a mathematical cost. The cost is high if the simulated output phi, using the transfer function, is far from the target phi, or if the actuator commands require too much energy, or if they violate hardware limits. Optimization algorithm. The compiler uses algorithms, gradient descent, adjoint methods, genetic algorithms, to search the vast space of possible command sequences for the one that minimizes the cost function. It's asking, what is the most efficient, safe, and accurate way to make this happen? 3. Scale bridging protocols, from macro to micro. The high-level program deals with objects like vortex, wave, gradient. The actuators work at the level of individual pixels or coils. The compiler must bridge this gap. Spatial decomposition. Create a vortex at xy must be broken down into, for each actuator, calculate the phase shift needed to create a spiral phase profile centered at xy. Temporal sequencing. Ramp up the field over 1 second must become, for each time step t from 0 to 1 second, set actuator command to value equals ramp function t. Constraint enforcement. The high level requires coherence BUMA x must be translated into a hard constraint in the optimizer's cost function, penalizing solutions that would require rapid, high-energy changes. The coherence budget, actuation fidelity, and hardware limits. Before compilation, we have a strict coherence budget defined by the hardware. 1. Actuator fidelity budget. Each actuator has a maximum faithful range. A speaker can only produce sound pressure up to a point before distorting. A laser can only shift phase within 0 to 2 pi. The compiler's solution must keep every actuator command within its linear, faithful operating window. The budget rule. No actuator command shall exceed 80% of its maximum rated value to avoid nonlinear distortion. 2. Slew rate bandwidth budget. How quickly can the whole actuator array change state? This limits the maximum omega, temporal frequency, of patterns we can create. The compiler must ensure the requested pattern does not require changes faster than the hardware can execute. The budget rule. The computed command sequences must have a frequency spectrum that lies entirely within the hardware's 3 dB bandwidth. 3. Sudden, large changes in actuator commands can cause power surges, heating, and mechanical stress. The compiler must smooth transitions. The budget rule. All command transitions must be differentiable, no sharp corners, and the maximum instantaneous power draw must be below the foundry's supply rating. The compiler optimization must respect these as non-negotiable constraints. The coherence gate and rollback trigger. The coherence gate for compilation is passed in two stages. Stage 1, mesoscopic simulation pass. What we measure: the simulated phi output from the compiled actuation sequence using the hardware model. Pass rule. The simulated output matches the target phi pattern within a tight error tolerance, for example, 99% correlation. The simulated actuator commands stay within all hardware budgets. Pass. The sequence is certified for testing. Fail rule. The simulation shows significant error, pattern instability, or budget violation. Fail. Compilation is rejected. The compiler must adjust its optimization parameters and recompile. Stage 2. Physical validation pass, micro rollback. After stage 1 pass, the compiled sequence is sent to the foundry to run in a highly instrumented, short-duration test. Hezbollah. What we measure: HLS calibrated phi field data from the actual run. Hezbollah. Pass rule. The actual output matches the mesoscopic simulator's prediction within the expected calibration error. This validates the hardware model. Full pass. The compilation is validated for this foundry. Fail rule. The actual output deviates significantly from the simulator's prediction. This indicates a flaw in the hardware model. Fail. This triggers the rollback trigger. The rollback trigger is a model update, not just a state revert. What we do: the test run is stopped. The new HLS data, showing the discrepancy, is fed back into the calibration loop for the hardware model. The model is updated. The original phi program must then be recompiled with the improved model. We do not proceed with the flawed compilation. A measurement scene: the vortex beam and the spatial light modulator. Let's enact our roadmap's measurement scene. Scene: compiling a vortex beam program for a spatial light modulator, SLM, a device that imposes a spatially varying phase delay on a laser beam. High-level program: create BB, type equals vortex, charge equals +2, waste range equals 1 millimeter. The compiler's task: translate this into a 2D phase mask, a grayscale image, to display on the SLM's pixels, where each pixel's gray value corresponds to a phase shift from 0 to 2 pi. The pass, good compilation. 1. Hardware model. The compiler knows the SLM's pixel pitch, the mapping from voltage to phase shift, calibrated, and the crosstalk between adjacent pixels. 2. Inverse solve, a charge +2 vortex. It then optimizes this ideal profile to account for pixelation, the fact that the SLM has discrete pixels, and crosstalk. The output is a refined phase mask. 3. Mesoscopic sim. It simulates light propagation through this mask. The simulation shows a clean, dark central singularity, the vortex core, with the correct helical wavefronts. Hezbollah 4. Safety rail. The phase mask avoids sharp 2 pi to 0 jumps between adjacent pixels, which the SLM can't do perfectly, instead creating smooth ramps. It respects the SLM's maximum phase shift limit. 5. Physical validation. The mask is loaded onto the SLM. The resulting beam is measured with a wavefront sensor. The measured phase shows a perfect +2 charge vortex. The energy in the beam matches predictions. Pass. Coherence gate is open. The fail, poor compilation. A naive compiler might just map the ideal spiral phase directly to pixels, creating sharp phase wraps. The mesoscopic sim might show significant distortions, but let's say it passes. On the hardware, the sharp wraps cause diffraction artifacts. The output beam is a blurry donut with no clear phase singularity. The wavefront sensor shows a messy, non-integer charge distribution. Or worse, the rapid phase changes demand too much from the SLM's liquid crystals, causing overheating and a slow, degraded response. The beam never forms correctly. Fail. The model was wrong. Didn't account for liquid crystal dynamics adequately. Rollback trigger. Update model with new thermal data. Recompile with a smoother phase mask that minimizes liquid crystal reorientation effort. The prediction spine. The hallmarks of a good compiler. A well-designed phi compiler yields a powerful prediction spine. 1. Efficiency gain. Compiled implementations will be more energy efficient and reach the target pattern faster than naive, hand-coded actuation sequences written by a human expert. The optimizer finds the global minimum of the effort-cost function. 2. Predictable refinement. The compiler's performance, accuracy, efficiency will improve predictably as the hardware model is refined with more calibration data. Each calibration run reduces the error bars on the model parameters, leading to a quantifiable reduction in prediction error in the mesoscopic sim. 3. Portability. Programs compiled for different foundries of the same type, for example, two different brands of speaker arrays, both properly calibrated, will produce functionally equivalent PHY outputs. The compiler abstracts away device-specific quirks, providing a layer of hardware independence. Falsifiability, when the bridge cannot be built. Our falsifiability threads test the limits of automatic translation. Falsifier 1. If a compiler, despite excellent models, cannot outperform a human expert, writing direct, low-level control code for a specific pattern in terms of accuracy, speed, or efficiency, then its optimization algorithms are failing to capture some essential physics or ingenuity that the human encodes intuitively. The compiler would be an inferior tool. If compiled code works perfectly in the twin and the mesoscopic simulator, but consistently fails on the actual hardware, beyond the margin of calibration error, then the compiler's hardware model is fundamentally wrong or incomplete. It is missing a critical dynamic, like thermal effects or nonlinear couplings. This would force a deep reevaluation of our ability to model physical actuation at the required level. These falsifiers ensure the compiler is a bridge of truth, not a tower of assumptions. Triunity in compilation. The compiler's work is inherently triune. Time echo, temporal optimization. The compiler schedules actuator commands in time. It solves for the optimal trajectory from initial state to target state, minimizing transients. This is control over omega. Space echo, spatial decomposition. The compiler maps the target pattern onto the spatial array of actuators. It solves how each pixel, speaker, or coil must contribute to the whole. This is control over K, the spatial texture. Motion echo, dynamics generation. By coordinating the time and space solutions, the compiler generates the desired motion in the phi field, the propagation of waves, the drift of defects, the flow of gradients. This is the emergent V. A compiler error in one echo dooms the others. A wrong spatial map cannot be fixed by perfect timing. A mistimed command can smear a perfect spatial pattern. Lanterns across scales, the universal translator. The compiler pattern is everywhere we turn intention into action. Near scale, robotic arm, motion planning. The program says, move the cup from A to B without spilling. The compiler, motion planner, models the arm's dynamics, transfer functions for each joint, solves the inverse kinematics and dynamics, optimization for smoothness and minimum jerk, and outputs low-level motor currents and trajectories. The phi field here is the configuration space of the arm. Middle scale, building climate control. The program says, maintain 21 degrees Celsius with 50% humidity in all zones. The compiler, building management system, models the thermodynamics of rooms and HVAC systems, solves for optimal valve settings, fan speeds, and chiller commands across time, and outputs the control sequence. The phi field is the temperature or humidity field. A hypothetical program says, increase atmospheric oxygen by 1% over a century. A planetary scale compiler would model climate, biosphere, and geoengineering actuators, solve for an optimal, stable intervention schedule, and output directives for forest management, ocean iron fertilization, etc. The phi field is the planetary chemical and ecological state. In each case, the compiler bridges the what to the how across a chasm of scale and complexity. The ethics of the compiler, responsibility in translation. The ethics of compilation is the ethics of faithful and safe translation. 1. Transparency of limitations. The compiler must output not just commands, but a confidence report. This compilation has a 95% predicted fidelity based on the model. The following hardware limits are within 5% of their maximum. Actuator Bank 7 slew rate. The user must know the risks built into the translation. 2. Safety by construction. The hardware limits and safety rails are not suggestions. They are hard constraints in the optimization. A compiler that produces commands exceeding these limits is buggy, even if those commands would technically work. Safety is compiled in. 3. Accountability via provenance. The final actuation sequence is tagged with the exact compiler version and hardware model version used. If a failure occurs, this allows perfect reproducibility and diagnosis. Was it a compiler bug or a bad model? The chain of responsibility is clear. Power without a faithful compiler is delusion. The compiler embodies the ethic. We will ensure our beautiful intentions are not mangled by the clumsy hands of our machinery. The recognition skill, seeing the compilation gap. You know you need this skill when there is a painful, manual, and error-prone process between designing something and making it happen. When a physicist calculates a beautiful magnetic field configuration on paper, and then an engineer spends weeks writing thousands of lines of LabVIEW code to approximate it on a coil array. When an architect designs a curved building, and the builders struggle to translate the digital model into instructions for the concrete forms. When a policy is written, and its implementation on the ground bears little resemblance to the intent. The moment you groan and think, if only the machine could just figure out how to make this happen, you're facing a compilation problem. The solution is to build a translator that automates that groan-worthy leap. The master tree location. This part, 10.3.4, is the keystone arch of book 10.3. It depends on the language, 10.3.1 for the source code, the twin and calibration, 10.2.5 for the hardware model data, and the foundry model, 10.4.0 for the context of the actuators. It is the final crucial link in the programming chain. It enables everything that follows in physical engineering. It unlocks adaptive control, 10.3.5, where the compiler can recompile in real time based on sensor feedback. It is the crucial bridge from software to reality for all of book 10.4 reality engineering. Without a compiler, programming is just poetry. With it, programming is potent. Return to the phi. Let us zoom out. We are translating desires expressed in the language of phi into physical nudges applied to the phi field. The compiler is itself a phi process, a pattern of computation whose output is a pattern of control signals whose purpose is to create a pattern in the world. It is phi manipulating itself through a chain of representations, each step governed by the need for coherence. The universe compiles the laws of physics into every instant of existence. We are building a tiny, local mirror of that process, focused on our specific, humble intentions. Zenodo and the equations of the compiler. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. The papers detail the inverse problem formulations, often as partial differential equation constrained optimization. The adjoint method for efficient gradient calculation in high-dimensional actuator spaces. The regularization techniques to enforce smoothness and hardware limits, and the convergence proofs for the optimization algorithms. They provide the rigorous mathematics that ensures the compiler's translation is not just clever, but correct and optimal. So, picture yourself in the translation vault. You type the simple command, create wave. You press compile. There is a moment of silent computation. The mesoscopic simulator lights up, showing a perfect wave converging to a point. The right side display floods with data. The orchestra's sheet music, perfectly notated. A status appears. Compilation successful. Predicted fidelity, 99.8%. Energy cost, 14.7 joules. Safe for execution. You have just witnessed a miracle of engineering, the seamless transformation of thought into actionable physics. You have learned the principles of the phi compiler, the final, faithful link in the chain of creation. This is part 10.3.4, phi compiler design and scale bridging, from intention to actuators. It is the completion of book 10.3, the moment programming becomes potent. In our final part of book 10.3, we will close the loop completely. We will introduce adaptive control, 10.3.5. We will learn to make the compiler dynamic, so it can listen to the real-time phi sensor data from the foundry, compare it to the target, and recompile adjustments on the fly to correct for disturbances, model errors, or unexpected events. We will learn to make our creations not just obedient, but resilient. Remember, one field, phi, with its infinite echoes. We can now not only speak to it and translate our speech, but we are ready to build the ears that will let it speak back to our machines, creating a true adaptive dialogue with reality. Salam and peace be upon you.